All right, so we had Newton's law of cooling. We had this nice formula going on there where lowercase t is the variable that defines the function. Uppercase T is your temperature in the room. Your U sub 0 is the initial object's temperature, whatever that object is. And then K is the cooling coefficient. That's different for each object, depending on what the object's made out of, sort of thing there. So what we're going to deal with here is this example. Got an object that was heated to 100 degrees Celsius, so this probably dropped in some boiling water. It heated it up to 100 degrees. And then it's allowed to cool in a room that's 30 degrees Celsius. And then if the temperature of the object is 80 degrees Celsius after 5 minutes, so our T in this problem is going to be in minutes. It's defined there in the problem. When will the temperature be 50 degrees? So with that, we got to do some work here to work with that. So when we start with our formula, we've got the original formula, and I'm plugging in the things that I know. Okay. From this problem, I know what temperature did the object start at. It started at 100 degrees, so that's U sub 0. Okay, so that's where this 100 is coming in right here. And then the room temperature, capital T, is 30 degrees because it said that in the problem. So there's 30 goes there. And then it said after 5 minutes, it's 80 degrees. So here's 80. That's the final temperature after 5 minutes. So the variable here is K. We don't know. They didn't give us a cooling coefficient for whatever object this was. So we've got to find it first. Okay, so we're going to have to do 2 problems to answer 1 question. Is basically what's happening here. So we've got a fairly simple exponential equation to solve. It looks kind of complicated because it looks like it's really big, but it's not if you just do the work to solve it. So to solve it, you could subtract 30, and there's 50, and that would be 70 e to the 5k. And then I would divide by 70 to get the e to the 5k by itself. Whoops. 5 over 7 e to the 5k. How do I get rid of the e? Natural log, yeah. So natural log of each side. And that's going to be natural log 5 over 7 is equal to 5k. Because remember, natural log and e cancel each other out. So it's just 5k. So one more step to get what k is. Divide by 5. So when I divide that by 5, I'm going to get k is equal to something. So I need to figure out what natural log of 5 over 7 and then divide that by 5. Negative 0.0673. Let's go 3 significant digits there. So there's my k value. Now what I've done is I've taken that and I went back to my formula for cooling, Newton's law of cooling, and I put everything else back in there. And instead of k, I put this number, and then t is back to being my variable. Because you didn't get a k value. If they give you a k value, you don't have to do that. They didn't give us a k value. They gave us a time, 5 minutes, and then they gave us a temperature after that 5 minutes. That's when I'm going to know I need to find k. If they say k equals and they give you a number there, you don't have to do that. So here they didn't give us that. They gave us a time and a temperature. That's how you're going to know. If they give you a time and a temperature, you're going to have to find k. That's how you're going to know that. Good question. All right, so here I'm going back to the original formula and plugging in. So the room temperature is 30, the initial temperature is 100. All that stuff's still the same. And then we got k right there. That's my cooling coefficient for whatever this object is. I don't know what it is. Doesn't matter what it is. Now, here's where we want to answer the real question that they ask in the problem was, when will the temperature be 50 degrees? That's what it asked. When will the temperature be 50 degrees? So we want to know, when will that equation equal 50? So we're going to solve it for t. We're looking for a time. How much time does it take to do that? So 50 equals 30. And you know, you can simplify that if you want to. And then just solve that equation for t. It's the same steps it took to solve for k. It's just got different numbers in there. Divide by 70. 2/7. What do you do to get rid of the e? Natural log again. Same game, just different numbers here. So I'm gonna come up here, give myself some room. Natural log 2/7 equals negative 0.0673 t. And then divide by that decimal there. Oh, we don't need the t, sorry. And then on this side. We want time, and that's going to be in minutes. It's not an exponent anymore because I took the natural log, and that natural log of e cancels out. So this is not an exponent now. It's brought down to the coefficient level, I guess is the right way to say that mathematically. So natural log 2/7 divided by negative 0.0673. 18.61 minutes. We'll go one to, we'll go 18.61 minutes. So with Newton's law of cooling, you know you're going to have a K value. Sometimes they're going to give that to you. They're going to say K, the cooling coefficient, or K equals. They're going to tell you that. If they don't tell you what the cooling coefficient is, or they don't give you the equation with it already plugged in there, that's when you know you're going to have to solve for it first before you can do the rest of the problem. They're going to give you a time and a temperature, and then you've got to find K, and then use that K value like we did here from here down. Okay. Different problems. This is the worst case scenario. They don't give you all of the stuff. A lot of times they're going to give you this equation to start off with, say, or they may have the capital T not plugged in. They'll have the K value plugged in for you out of that. So just different parts, that they're going to give you there. Let's talk about the logistic model. It's this little formula here, and guys, I'm gonna provide you some a lot of the problems that you're gonna encounter have the equation already written for you. So but the cooling Newton's law of cooling formula, I'm gonna definitely give that to you, and probably the financial models as well. But all right, so here's our logistics model. Let's talk about population. C on top here, just a number. It's the carrying capacity for a system. It's we're dealing with things like, I think one of the examples that we'll do is like fruit flies. I don't know if y'all had biology, did the fruit fly experiment where you try to. There's only so many that can live in a certain environment. That's the carrying capacity. So the carrying capacity is how many can this environment sustain, that sort of thing, before they all die off. And then all this other stuff, you got e to an exponent of negative b over t. This stuff is going to be given to you. You're not going to have to find this thing. They're going to tell you what these numbers are. But with the logistic model, they're probably going to give you the equation like example D. You got the equation, and they're going to ask you some questions about it.
Well, what if they don't give you the equation? How are you supposed to know
They're going to say this follows the logistic model. This follows the with the financial stuff, you're going to know it's financial stuff because it's going to say invested so much money at a certain rate or something like that. So they'll say, this situation follows the logistic model, and then you would know that they're going to give you the equation of the logistic model. Almost every one of them that I'm going to ask you to do anyway. All right, so here are some of the questions they might ask. They give you the equation, P of T equals 230 over 1 plus 56.5 e to the negative 0.37 t is what that is. So 230 over 1 plus 56.5 e to the negative 0.37 t is our equation that they case.